In the late autumn of 1833, a violent storm lashes the south coast of England. Deep black clouds race low as howling wind and rain drive horizontally against the cliffs. Lightning rents the sky, illuminating, just for a moment, a lone figure battling against the gale. Skirts billowing in the deluge, she picks her way carefully between mighty hewn rocks on the seashore, occasionally pausing, backtracking. She is searching for something amidst the sands. Just ahead of her, the now saturated rocks of a mighty cliff face begin to crumble against the storm's relentless assault. Splitting and crashing down onto the beach below, accompanied by their own thunderous din, death for anyone unfortunate enough to stand below. But our figure doesn't flee from the danger. As the dust settles and the rain begins to ease, she calmly, determinedly strides forwards towards the cliff's wreckage. Atop massive, shattered boulders, she stoops to peer at the fresh surface of limestone at her feet. And on that surface, embedded within it, an eye peers back at her. The hollow eye socket of an ancient, prehistoric sea creature entombed in the earth for 200 million years. In this way, Mary Anning, the daughter of a cabinet maker, became one of the first and most influential paleontologists in history. This wasn't the first skeleton from the deep past she'd uncovered, and it wouldn't be the last. Ichthyosaurs and plesiosaurs, contemporaries of the dinosaurs, being found in southern Britain in abundance. Once a shallow sea, home to a vast diversity of life, all those millions of years ago. Today we know this starkly beautiful landscape as the Jurassic Coast. In order to find fossils here in the decades before Darwin, Anning battled not just the British weather and poverty, but academic indifference too. For then, creationism still reigned supreme. Not to mention, as a woman in the early 19th century, it was nigh impossible for her achievements to be recognised by the overwhelmingly male-dominated scientific community. Nevertheless, today she is widely credited with some of the earliest discoveries of ichthyosaurs, plesiosaurs and pterosaurs, helping to revolutionise the growing field of paleontology in the process, as well as spawning a popular nursery rhyme. Doubtless, Mary Anning's discoveries were remarkable, and though old, the fossils she found are a mere 200 million years old. They document a Jurassic world, where dinosaurs ruled land, air and sea. With more than 3 billion years of evolution preceding them, they are a late chapter in the story of life on Earth. What then of these preceding years? What records do we have of the organisms that lived before? Can we find the first pages of the Book of Life, the fossils from the very first chapter, when life was just getting started? Tracking down these first fossils has taken 200 years of paleontological discovery and study. Scientists have scoured the globe, developing brand new techniques in a singular quest for this undiscovered tome. What began with Mary Anning braving the English weather in order to make a living from selling stones, continues to this day, a search for the very earliest fossils of our world. Aside from the challenges Mary Anning faced in finding recognition for her discoveries, her job was a relatively easy one. The fossils she sought were large, well-preserved, and abundant in the limestone cliffs near her home. When she uncovered a fossil skull, like other scant references of colossal monsters pulled from the earth in antiquity, it was clear from its appearance that it was indeed a skull, albeit of some mysterious creature long extinct. But the deeper in time paleontologists probe, the harder their task becomes. The further back in the record we go, the creatures become increasingly bizarre, until it becomes ever more difficult to distinguish fossil from rock. Particularly past 500 million years ago, when life becomes much more simple. What traces can we expect to find of some of the earliest life on Earth, billions of years before our time? In order to do so, we must consider exactly how a living organism comes to be immortalized in rock at all, encased in a tomb of 1 billion years. When a living organism, be it animal, plant, or even microbe, dies, biological and chemical agents move quickly to devour it. Fungi and bacteria recycle the precious carbon, breaking down soft tissues and leaving nothing behind. For creatures with hard parts like bones, teeth and shells made from minerals like calcium and phosphate, these are a bigger challenge, but eventually these too are broken down to serve the great cycle of life. So, to be preserved as a fossil, a dead creature must be entombed, sealed away from these ruthless scavengers before they have a chance to act. Organisms that fall into sediments deposited at the bottom of oceans, lakes, rivers and marshes stand the best chance of escaping consumption. Surrounded by mud and sand, these remains are buried deeper, and gradually, as geological forces kick in, loose sediment is transformed into solid rock. Any organic structures within become a template for petrifying minerals, preserving the shape of the long-dead organism as rock within rock. In this way, the remains of once verdant forests, millions of years old, can be seen all over the Earth. Yet despite their apparent permanence, rock repositories are not immortal. Over vast periods of geological time, tectonic forces shift landscapes around the Earth's surface, folding solid rock, plunging fossils deeper or raising them into high mountain ranges. The rocks and the long-dead life forms within are crushed, cooked, and contorted out of all recognition. Sometimes they are destroyed altogether, subducted and melted at the base of the crust, or shattered by the elements they're exposed to at the surface. Therefore, the older a rock, the more of these convulsions it will have witnessed down the eons, and the more likely it is for it to be altered or destroyed. In other words, the older a fossil, the rarer it becomes. In fact, the odds of finding a fossil of the earliest life on Earth are vanishingly small. That organism, whatever it was, must have ran a 4 billion year gauntlet of chemical and biological scavengers to avoid decay. Without any mineralized shell or other hard parts, its inert organic matter must have been entombed within a matter of mere hours. The right minerals must have been present to encase and preserve the delicate, minuscule structures within the accumulating sediments. And then, when the rock is formed, it must withstand billions of years of tectonic activity without alteration. Through the creation and destruction of continents, the rise and fall of oceans, too much heat or pressure or alteration at the surface all threaten the faint echoes of early life locked inside the crust. Discovering those first echoes, those first fossils, is a tall order indeed. In the search for the earliest fossils on Earth, paleontologists must look within the oldest rocks. And yet, though the Earth is more than 4.5 billion years old, there are only a handful of places on Earth where rocks older than around 3 billion years remain. Even rarer are places where the rocks haven't been cooked or squeezed beyond all recognition. One of those places is in the brutally arid badlands of Western Australia. Named North Pole by the 20th century miners who once toiled here, a reflection of its stark remoteness. But in all other respects, this patch of the Australian outback could not be further removed from its Arctic namesake. This is a desolate landscape, with one of the hottest climates in all of Australia. Dusty red terrain studded with rounded tufts of spinifex grass, innocuous at first glance, but laden with tiny silica needles that rip into clothes and skin. Fieldwork here is treacherous, and geologists rarely wander far from their reinforced four-wheel drives, lifelines to the outside world. There are no roads out here, and this is kangaroo territory. Yet this barren landscape is a great benefit to the prospecting paleontologist. With little water and vegetation, the rocks are exposed and in good condition. And among them, a kind known as apex cherts. They are dark-coloured, glassy rocks made of almost pure silica, with a little carbon trapped inside. They formed from a kind of gel that accumulated on the sea floor long ago, under conditions very different to today. The nearby rocks help to add context to these mysterious ones. Reconstructing them reveals an ancient, shallow sea surrounded by volcanic islands. The cherts formed on this prehistoric sea floor amidst hot, mineral-rich hydrothermal fluids, circulating upwards from roiling magma chambers within the crust. And by measuring the isotopic ratios of minerals in the surrounding volcanic rocks, geologists can pinpoint the precise age of the cherts. 3,465 million years old. This is an extremely rare window on an Earth just 1 billion years old, a time when much of what is now Australia rested on primordial sea floor. The vast age and excellent preservation of these ancient apex cherts is remarkable, but that's not all that makes these rocks special, for they also contain the oldest direct evidence for life on Earth. The first fossils. Since life at this time, 3.5 billion years ago, is still finding its feet, it hasn't yet advanced beyond the microscopic. In order to find those fossils, paleontologists examine paper-thin slices of the chert with powerful microscopes. Embedded inside the chert, asteroid crystals of silica sit tiny structures made from flecks of carbon. Tubes and hollow balls, each 1/100th of a millimeter across, sometimes arranged in chains. They are remarkably similar in both shape and size to modern bacteria. Just like Mary Anning's vertebrate fossils were similar to living vertebrates, so these microscopic structures are similar to microbes that live today. However, simply matching shapes isn't enough to prove that these scraps of carbon were once alive, especially when the shapes themselves are so simple. With the label of oldest fossils hanging in the balance, they must be proved beyond all reasonable doubt to have been created by biology rather than the inanimate Earth. Carbon itself doesn't signify life. It is an element born in space, within the molten core of stars, and is distributed all over the Earth in various forms. Chemical transformation can create specks of black carbon, like those in the apex cherts. As for the shapes, tubes and balls are not complex forms, and could be created by entirely abiogenic processes. It's practically impossible for physics and chemistry alone to create an ichthyosaur skull, but a simple microscopic ball of carbon isn't so hard. As crystals of silica grow, they can push the specks of carbon along at their edges, gathering and concentrating them. When many crystals join, the carbon at their margins begins to resemble filaments and nodes that look remarkably like these putative microfossils. So, in order to verify the structures as created by life, we need more supporting evidence, more clues that point to the hand of biology in these ancient rocks. The first hint can be found by taking a step back from the microscopic world of carbon tubes and balls to examine the larger scale structures of the cherts around North Pole. Because these glassy rocks aren't uniform and featureless. In places, they're made up of fine layers that sometimes bend and buckle upwards. These structures are reminiscent of stromatolites, layered dome-shaped structures built by mats of bacteria as they grow from the sea floor, stretching upwards towards the light. Today, modern stromatolites are rare and are only found in any numbers, coincidentally, on the western coast of Australia at Shark Bay. Elsewhere, grazing animals destroy these bacterial megastructures before they can take hold. But in the ancient seas, without grazing animals, stromatolitic metropolises were much more common. Finding their characteristic dome-shaped fossils hints at the thriving microbial community that gave them form. But there are other processes that can create similar laminations in ancient rocks, and which don't necessarily need microbial intervention. Domed layers on the apex cherts do not on their own imply life, but their abundance alongside the carbon microfossils strengthens the case. A final clue to corroborate life comes from chemistry. Interpreting the chemical compositions of such ancient rocks is fraught with difficulty. as alteration over billions of years or contamination during study can completely change the result. So it's taken decades of careful, high-precision testing to uncover what scientists now consider to be the smoking gun for life in the apex cherts. It's well known that life is picky when it comes to its carbon. On Earth, there are two stable forms of carbon with different numbers of neutrons in their nuclei. Carbon-13 is very slightly heavier than carbon-12, and living things preferring the easy option will preferentially pick the lighter carbon for use in its cells. So, scientists can measure the ratio of carbon-13 to carbon-12 in organic matter and find it's relatively depleted in carbon-13. And when paleontologists measure the ratio of carbon-13 to carbon-12 in the organic structures of the apex chert, they find that these, too, are depleted in the heavier version of the element. Something has favoured carbon-12, and that something is likely life. Just as with the stromatolite-like layers, life isn't the only thing that can fractionate carbon in this way. There are some obscure chemical processes that favour the lighter form. Alone in such ancient rocks, this chemical signature would still be up for debate. However, alongside the carbon microfossils and the domed layers, the characteristic carbon ratios help to make a compelling case for life. Now, after years of fieldwork in the unforgiving Australian outback and decades of rigorous study and cross-examination, scientists have reached a consensus that the apex cherts do indeed contain the earliest fossils on Earth. But what of the first billion years of the Earth? Today, the fossils in the apex chert show us that even 3.5 billion years ago, life had colonized enough of Earth's shallow seas to begin leaving a trace. They may be the earliest fossils, but they are by no means the earliest living things. So could there be a record of even earlier life yet to be discovered? If there is, it will be even more difficult to track down and verify than the apex microfossils. Older rocks are incredibly rare and invariably more tortured, twisted out of all recognition. And besides, the biology we are looking for is even more simple and harder to distinguish from mere chemistry. But that hasn't stopped paleontologists from trying. Although no other place brings together discrete lines of evidence like the apex chert, there are tantalizing hints that could point the way to an earlier fossil record in even more ancient rocks. Not far from the outcrops of apex cherts, near North Pole in Western Australia, there are rocks that are around 15 million years older than our oldest fossils. These are not cherts, however, but layered sedimentary rocks, such as might be deposited on a coastal mudflat. And within these rocks, on the ancient mudflat surfaces, are tufted patterns and textures, which scientists believe were produced by microbial mats. We still find mats like these in estuaries today, not so extravagant as a domed stromatolite, but extensive nevertheless. Although the textures in these older rocks are compelling, there is no prospect of additional clues here. Although sediments were deposited rapidly enough to make moulds and casts of the mat's patterns, conditions weren't conducive to preserving the organic fossils themselves. The microbes that formed them were recycled back before they could be embalmed in silica, disappearing back into the ether. similar structures were recently revealed in even more ancient rocks. This time near the original North Pole. Greenland, a land that couldn't be more different to Western Australia, is famed for its ancient rocks, but until recently they were not considered a good prospect for paleontology. The ISUA greenstones are among the oldest rock outcrops in the world at 3.7 billion years old, but they are metamorphic. They have been crushed and cooked beyond recognition, and hints to their original composition have been lost forever. But in 2016, newly melted snow revealed an unanticipated treasure, a section of the ISUA rocks that had somehow escaped the destructive transformation. Here, the rocks preserved some of their original sedimentary features, and among them, curious, conical structures that some scientists interpret to be the beginnings of stromatolites. Unfortunately, although the structures have escaped the ravages of time, the organisms, if they were indeed involved, have not. There is no organic matter left in the ISUA rocks, and the chemical signals, so clear in the apex cherts, are controversial in Greenland. With such little information, the case remains open. An even more tenuous hint can be found not in rocks but inside individual minerals. While the most ancient rocks may have been destroyed by uplift and erosion, some vestige of them remains in especially resistant materials called zircons. Zircons can be plucked out of an older rock as it wears away, to then be incorporated into younger sedimentary rocks as they form. One such zircon was discovered, like so many ancient paleontological clues, back in Western Australia. Although the rocks from which it was collected are around 3.3 billion years old, the zircon, recycled from an older source, is much older. It formed 4.1 billion years ago and contains tiny flecks of carbon trapped as the crystal grew. That carbon contains the characteristic depletion of heavier atoms, known to be created by living things. It's a sign that life was already fractionating carbon more than 4 billion years ago. But a single mineral can contain no further information. There are no microfossil structures, only isolated flecks, and there are no layered rocks, only this one surviving time capsule from an unimaginably ancient Earth. On its own, the smoking gun is little more than just smoke. More recently still, scientists reported microfossil-like structures in the rocks of northeastern Canada. These rocks appear to be deposits from ancient hydrothermal vents on the sea floor, and have only been slightly metamorphosed, so some of their original features remain. Within them, there are tubes and filaments formed from iron minerals that are very similar to modern-day microbes and younger fossils in these settings. But no carbon remains, and the discovery is stymied by another problem. We can't be sure how ancient the structures really are. Age estimates for these rocks span 500 million years. If they are biological in origin, they could be 3.8 or as much as 4.3 billion years old. Such uncertainty and the lack of other evidence stands in the way of these putative fossils replacing the apex cherts on the podium. So, for now, our safest bet is with the apex chert. Although scientists continue to scour, test and probe the rocks in every inhospitable corner of the globe, searching for even deeper echoes of life on Earth. With the next snowmelt or rockfall, we hope to discover more tantalizing clues to the mystery of life's origin on our planet. Next time, we investigate the immense, invisible magnetic forces which shaped and continue to shape our world. You've been watching the entire history of the Earth. Don't forget to like and subscribe, and let us know what you think in the comments. We'll see you next time.